Thank you for visiting my channel. I am the Actuarial Guy. This is a continuation of Unit 2 and we will be looking at compound interest. Well, in the case of compound interest, interest itself earns further interest. Now suppose an amount C is deposited in an account that pays compound interest at the rate I by 100% per annum. Then after n years, the deposit will have accumulated to this to C into 1 plus I raised to the power n, where C is the amount deposited, I is the rate of interest, and n is the time in years. You may be wondering how this formula comes about, and if you're interested in learning how we can generate the formula, just drop me a message and I'll do a quick video just for you. Well, to make that idea clearer, you're going to look at an example where someone deposits £1,000 into a bank account that offers compound interest at the rate of 4% per annum for a period of 2 years. So how much does this guy accumulate at the end of the 2 years' time? Well, we have our formula here, which we saw in the previous slide. Our C is 1,000, our N is 2 years, and our I is 0.04. Remember, this rate of interest is given in the form of I times 100%, where 4% per annum simply means that I is equal to 0.04, such that if you say 0.04 times 100%, you come up with 4%. So we plug these values into this formula and we end up with a final value of £1,000 and 81 £1,081 and 60p. Then now we go on to accumulation factors. What I want you to do is to consider two time periods. I want you to think of a time T1 and T2, where a time T1 can be less than or equal to the time T2. Now we'll use these two times to define an accumulation factor. This here, this is defined as an accumulation at time T2 of an investment of 1 made at time T1. What I simply mean by this accumulation factor is that like in our compound interest example, we have an amount C and this amount accumulates to a certain value after 2 years. This amount C is constant, but it is accumulated by this bit here. So when you take this bit, plug in the values and work out what this is, in effect this is your accumulation factor. You multiply that with the amount of money to find out what the total accumulation is. So in other words, the bit I just showed you is what is given here, and it's called the accumulation factor. So a question here, what is the accumulation at time T2 of an investment C made at time T1? Quite simply, you write down your accumulation factor, investment at time T1, what's it value at time T2, that's your accumulation factor, and to find the accumulation you simply multiply it by the value of the investment. So if you invest, this C could be 500, 1000, whatever you're investing, and then this bit here is your accumulation factor. What is an accumulation at time n of an investment of 1 made at time 0? This is simply, you write down your accumulation factor. The accumulation is made at time 0 to time n. There you have it. But this can actually be written as this AN in short. Now we're going to look at the principle of consistency. In order to help you understand the principle of consistency, I want you to consider a time series where we have time t0 is less than or equal to time t1, which is less than or equal to time t2, which is less than or equal to all the way to time tn minus 1 and time tn. Now, what the principle of consistency says in plain words is that if you have a certain sum of money and you decide to invest it such that you're investing it from time t0 to time tn, it doesn't matter whether you consider this accumulation from t0 to tn, or let's say you consider an accumulation from time t0 to tn minus 1 multiplied by an accumulation from time tn minus 1 to tn, or you consider maybe another accumulation from time t0 to time t1, you multiply it by an accumulation from time t1 to time tn minus 3 multiplied by an accumulation from time tn minus 3 to time tn. They are all equal. It doesn't matter what course of action you take. This accumulation gives you the same amount at the end of the day. So what the principle of consistency basically says is that in a consistent market, the proceeds should not depend on the course of action taken by the investor. Alright, we are now going to look at present values. Well, you've probably heard people say that $1 today is worth more than $1 tomorrow. What that simply means is that if you're given $1 today, or if you're given the same dollar tomorrow, it is not the same thing. You could take this dollar today, put it in a risk-free investment, earn interest on it, such that at tomorrow you will have slightly more than what you had. So your dollar tomorrow is going to be more than what it was when it was given to you. Hence they say $1 today is worth more than $1 tomorrow. Anyway, we know that an investment of C today made at a rate I times 100% will accumulate to C into 1 plus I n at time n. That is taking the compound interest model into account. So if I draw a time scale here, at time 0, if you invest C, you will end up with this at time n. So the question is, what is the value of an investment of this amount? Let us consider this amount. Let us say, take this investment. So you ask yourself, at time 0, an investment of C will give me this at time n. But what is the value of this investment at time 0? Well, you can clearly see here, it's already given to us. The value of this investment at time 0 is C. But how do you get back there? You get back there by taking your investment in future and discounting it back to the present, such that that cancels out and you end up with C. That is a discounted investment. So what is the value of let us think of another idea here. What is the value of an investment of C made at time n today? What is the value of C at time n today? Same as before, this value, considering that it is made at I times 100% rate of interest, the time period is n years, and you're considering compound interest, then this will simply be C over 1 plus I raised to the power n. That will be the value of this investment at time 0, which we can consider to be the present time. So we say that the discounted present value of C due at time n is given by this. This is its present value. The present is time 0. You just take it back here. Alright, so what we're going to do next is we're going to define a certain special quantity, and we're going to call it nu. We're going to say nu is that 1 plus I, such that 1 over 1 plus I raised to the power n is equal to nu power n. So if we look back here, this quantity here is equal to C by nu to the power n. So in what I'm saying here is that the discounted present value of C due at time n is given by that. Alright, discount rates. We can also obtain discounted value of a payment by using discount rates. Now we've got the simple discount and the compound discount. Like in the simple interest case, the interest earned itself is not subject to further interest. Now suppose an amount C is due after n years. You need to pay an amount C at time n at a rate of simple discount of D per annum. Then the sum of money required to be invested now to amount to C after n years, i.e. the present value of C, is given by this formula, where C is the amount invested, n is the number of years, and D is the simple discount rate. I will do a few examples in another video to help you understand this idea better. Now in the case of compound discount, as has been seen with the compound interest, the interest earned is subject to further interest. So suppose an amount C is due after n years, again, n years, an amount C here, and the rate of compound discount of D per annum applies, then the sum of money required to be invested now to accumulate to C after n years under compound discount is given by this formula, where again C is the amount invested, D is the compound discount, and n is the amount or the number of years. All you have to do is plug values into this formula and you will not go wrong. Once again, thank you very much for watching this part of my video, and I will go on to the next section, which has to do with the next section has to do with effective rates of interest and discount. Thank you very much for watching. Once more, I am the Actuarial Guy.